Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 5th, 2026, about 12 days ago. It presents a compact, high-throughput image editing pipeline that uses a 2 billion parameter QN3VL model and a 1.6 billion parameter SANA 1.5 model to match or exceed the performance of substantially heavier baselines. The paper is titled Vibe, Visual Instruction-Based Editor. And as we'll see later, the results are really impressive given that it generates high-resolution images in approximately 4 seconds. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, you will find Vibe with its 1.6 billion and 2 billion parameter models, plus code examples to start editing images using text instructions right away. Figure 1 displays a gallery of edits produced by the model. In the top left, the system adds a patterned scarf to the woman's neck. Crucially, her face remains unchanged, illustrating the strict source consistency the authors emphasize. Moving to the right, the cat example shows complex style transfer, turning a real animal into a robot. Finally, the large wooden box demonstrates background replacement, swapping grass for water while preserving the clock's intricate details perfectly. Figure 2 extends these examples to show even more dramatic style and medium changes. In the third row, we see a bird reimagined as a crystalline geometric figure on the left, and a blazing elemental creature on the right, proving the model can handle diverse artistic directions. Below that, the system demonstrates texture synthesis by turning a flat tarot card illustration into a detailed three-dimensional relief. Finally, the landscape on the left shows a complete atmospheric overhaul, swapping a sunny sky for an apocalyptic storm while keeping the terrain layout intact. Figure 4 details the architecture, split into a conditioning stream on top and a generation stream below. In the top branch, the input image and prompt are combined with learnable meta-queries inside the frozen QN3VL model. A trainable connector then adapts these features to guide the diffusion process. Below, the system encodes the original image and fuses it with the noisy target using channel-wise concatenation. This concatenation strategy is crucial because it avoids increasing the sequence length, ensuring the diffusion transformer on the right remains efficient during generation. So having set up the architecture, Table 1 outlines the 4-stage training recipe. In Stage 1, connector alignment, the system trains only the connector and meta tokens at 512 resolution, using purely text-to-image pairs, essentially teaching the components to talk to each other. Then, Stages 2 and 3 introduce the diffusion transformer into the training loop and ramp up the resolution to 1024 and then 2048 pixels. Notice how the data mix shifts here. Pre-training leans on text-to-image data to establish stability, while supervised fine-tuning flips the ratio to prioritize editing triplets. Finally, Stage 4 polishes the model with preference alignment, updating the diffusion backbone using strictly preference pairs. With the training complete, Table 5 reports the model's performance on the G-Edit benchmark. The columns here track semantic consistency, perceptual quality, and the overall score. Notably, Vibe achieves a semantic consistency score of 7.91, placing it second among all methods, and ahead of heavier baselines. While its perceptual quality score of 6.33 is lower than top models like Z-Image, the paper argues this reflects a design choice to prioritize faithful, minimally invasive edits over aggressive redrawing. While the previous table focused on general consistency, Table 4 digs into specific editing tasks on the G-Edit benchmark. The columns here represent different operations, ranging from adding objects to changing styles. Looking at the bottom row, Vibe achieves an overall score of 3.85, ranking second among all methods. It performs exceptionally well on tasks that require keeping the original image intact, leading the field with scores of 4.42 for remove and 4.22 for background edits. However, performance drops to 2.75 in the action column, likely because complex geometric changes are harder for the compact diffusion backbone to handle. Wrapping up, 2 takeaways stand out. First, Vibe proves that smart architecture and clean data can rival massive models, delivering high-quality edits on standard hardware in just seconds. Second, its focus on source consistency ensures edits look natural rather than hallucinated, pointing toward more accessible, efficient generative tools. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.